All right, so given this, this graph here, we've got a graph of a function and we want to draw its derivative and second derivative. And these graphs are written more in the language of calculus rather than the language of physics. But if f represents position, what do we call the derivative of that? The first derivative, first derivative of position would be velocity. And then the second derivative?
Acceleration.
Yeah, second derivative is acceleration. So a graph of position, a graph of position versus time, velocity versus time, and acceleration versus time literally are just the graphs of some function, its first derivative and its second derivative. In this case, we've got a graph of the function. In other words, we're interpreting that as position. And we want to rethink that as a graph of velocity and a graph of acceleration. And I would recommend, generally, the first thing I would recommend doing is if you got some weird looking graph like this, split it into portions of time that are just easily recognizable types of functions. For example, if we want to, this is from, let me put a link to it in the chat. This is, if you go to math.ncheese.org/P7math, Physics 7 Math Review, there should be a worksheet on derivatives and a worksheet on integrals. This is from the worksheet on derivatives. So here we've got the function itself, and we want to know what the derivative is. That is, what's the velocity at various different times. So I would say usually the first thing you want to look for is splitting up the position graph or whatever graph you have into regions that are easily recognizable types of functions. Like for instance, for the first 1 second, from 0 seconds to 1 second, that's pretty clearly a diagonal straight line. That's going to be easy enough to analyze. So I'm just going to put in a border at 1 second on all three graphs, just to split up the timeline. From 0 seconds to 1 second, it's behaving in a very predictable way. And then from 1 second to what would be the next time where we'd probably want to put in a border here? What's the next time? Yeah, 3 seconds, something's changing. So if we consider from 1 second to 3 seconds, on that entire time interval, we've got this very predictable flat line. It's just a constant position. And then maybe from 3 seconds to what's the next important change? Yeah, it looks like at 5 seconds, it stops being a diagonal line and starts being some sort of curve. So that's probably another important instant in time we want to consider. And then we get this curve that looks like, I don't know, maybe a cubic, maybe a sine function, maybe a couple of different parabolas. It's hard to tell exactly what curve that is, but we can at least mark some important points on it. It looks like we have, for instance, at 6 seconds, we have a 0 or a minimum, a flat point. So at that instant, it looks like the curve flattens out and it reaches a minimum. And it looks like at 9 seconds, the curve flattens out and reaches a maximum. And also something important is going on somewhere in between. It's hard to tell exactly where, maybe around 7.5 seconds. But it's around 7.5 seconds, the curve is changing in a very important way. It's changing from curving like this to curving like this. So what do we call that? Have you seen that sort of phenomenon before in calculus?
Inflection point?
Yeah, this looks like an inflection point. We're changing the concavity. We're changing from concave up to concave down. And anytime you're changing from concave up to concave down or vice versa, that's an inflection point, and that tells you something important about the other graphs as well. So I'm going to mark that too. Again, not really always easy to tell exactly where the inflection point is, but it looks like somewhere around 7 1/3 or 7.5. So by marking all of these important instants in time, it's going to be a lot easier to build the velocity graph and acceleration graph. Because now we can just take a look at, for instance, what's going on between 0 seconds and 1 second, what's going on between 1 and 3 seconds, and so on. For example, for velocity from 0 to 1, what does the velocity tell you about the position graph? What is velocity? Yeah, the position graph looks like it has constant slope, and so we should expect constant value for velocity. Since velocity is literally just the slope of the position graph, the rate of change. If the position graph is a straight line, the velocity is going to be constant because a straight line has constant slope. So we should expect velocity to be just some constant value. And would you expect that to be a positive constant or a negative constant or 0? Yeah, it should be positive. This position graph has a positive slope, positive constant slope, so velocity is a positive constant value. And we don't really have numbers for the vertical axis here, so we're just going to pick a value. So some positive constant value. Make that a little thicker so we can see it more easily. Let's use a different color too. So some positive constant velocity. And then what about from 1 second to 3 seconds? What's the slope of position there? Yeah, 0 slope. So that means we have 0 as the value for velocity during that period of time. And what about from 3 seconds to 5 seconds? Yeah, it should be negative and still a constant because it's a constant slope here. So negative constant slope on position means negative constant value for velocity. Since this looks a lot less steep than from 0 to 1 seconds, we should also treat this as a value closer to 0. So it's going to be negative, but not very negative. Maybe something like that. So that's the velocity graph during this period of time. And then the velocity graph is going to get more complicated because from 5 seconds on to 10 seconds, the velocity is not constant since the position doesn't have a constant slope. But there are some important things we can mark. We know, for instance, that at 6 seconds and 9 seconds, we've got a minimum and a maximum. What's the slope at a minimum or a maximum? Yeah, anytime you've got a minimum or a maximum, if the graph is hitting a minimum value or hitting a maximum value, then at that location, the tangent line is flat. In fact, you could even see this if you just look at like tangent lines, like let's say tangent line. But at this point, the tangent line is flat. Tangent line being flat means we have 0 velocity, or 0 as the derivative, which in this case is velocity. So we know at 6 seconds, the velocity must be 0. And at 9 seconds, the velocity must be 0. And then we can take a look at the in-between regions. Let's say from 5 to 6. What do you notice about the velocity? Or that is, what do you notice about the slope of the position graph? It's going to approach 0. It's got to get to 0 by the time we get to 6. What about before we get to 6? Like between 5 and 6, what do you notice about the slope? Would that be positive or negative? During this period of time, is the graph increasing or decreasing as we go from left to right? Yeah, decreasing, so that's going to be a negative slope. So we know that the velocity, even though we don't have exact values, we know that the velocity has to be a negative in this interval of time. And it's going to be not a constant because this is not a constant slope. We can expect it to start off as a large negative because we have a very steep slope to begin with, and then become closer and closer to 0 because it's got to reach 0 by the time we get to time 6. What about from 6 onwards? Yeah, From 6 onwards, the position graph is increasing. We got a positive slope on the x graph. So that means a positive value on the velocity graph. But again, it's not constant. We don't have a constant positive slope. We've got a positive slope that starts off at 0, then gets a little big and then bigger, and then gets flatter again. Because by the time we get to 9 seconds, we got to be back at velocity 0. In fact, after 9 seconds, from 9 to 10, the velocity has to be what sort of value? After 9 seconds, looks like the position's decreasing again, right? So the slope is going to be what sort of value? Yeah, we're back in a negative. So even though we don't have values, we can at least say the velocity has to be negative from 5 to 6 seconds, positive from 6 to 9 seconds, and then negative again from 9 to 10. Also, you can tell from the curvature here, it looks like we've got, if we actually try drawing this out, and this isn't necessarily going to be exact, but just the best we can do in the circumstances. It looks like this position starts off with a very steep downward slope. So we're going to start with a very negative velocity. And then the position graph becomes less and less steep. So the velocity graph is going to be changing, getting closer to 0. Position graph becomes more and more steep until we get to the inflection point, and then it becomes less and less steep. So velocity is going to increase positively until it gets to the inflection point, and then it's going to go back down because it's got to hit 0 by the time we get to 9 seconds. Then after that, it looks like the position now has a negative slope, so velocity is now negative, starting off just a little bit negative and then getting more and more negative. Something like this. So I think this is a reasonable sketch for the graph of velocity based on how the position graph's slope is changing from very negative to a little bit negative to 0 to a little bit positive to more positive to less positive to 0 and then back to negative again. So likewise, the velocity graph goes from very negative to a little bit negative to 0 to a little bit positive to more positive to less positive to 0 to negative again. So I think this is a reasonable sketch for the derivative of the original function. In other words, the velocity as time passes. Any questions on that velocity graph so far?
I have a question.
Mm-hmm.
For after we do the horizontal line at 4 and then between 5 and 6, why doesn't it go from 4 to 0 at 6, if that makes sense? Like, why does it start as another line underneath that horizontal line?
You mean why is there this sudden change in velocity at 5
Like,
seconds?
why wouldn't you just connect it and then make it go to 0 at 6?
If you take a close look at what's going on with the position at 5 seconds, the position is changing from a moderate downward slope to a very steep downward slope very suddenly. That sharp corner is really what tells us what's going on here. If you focus on this portion right here, if you have a sudden change in slope, like here we've got, it's a little bit steep and then suddenly changes to really steep. It's got that sharp corner. That's a sudden change in the slope. So we should expect a sudden change in the value of its derivative, changing from a little bit negative to really negative all of a sudden. So sharp corners like that signify a sudden change in the derivative. In fact, that's the same thing as we saw at 1 second and 3 seconds. At 1 second, we're changing from a positive slope to 0 slope suddenly. And likewise, at 3 seconds, we're changing from 0 slope to a negative slope. There's not really a transition. For these to be connected, we would expect that the slope to be changing more gradually, to change from like downhill to gradually getting more downhill. If it's changing from a little bit downhill and then suddenly changes to a very downhill, that sharp corner means there's a sudden change in the derivative. And that's not very realistic, by the way. Realistically, we would expect the position function to be curving a little more gently, not a sudden sharp turn. Any questions on that so far?
Okay, that makes sense. And then also, how did you know that you would have to make like curved lines for between 6 to 10? Like, are straight lines also okay? And then identify like a point at the top, or does it have to?
Possibly. The thing is, though, that this is, you would generally only get a straight line from a parabola, because the derivative, if we're looking at this in terms of the calculus here, if x is a quadratic function, let's say a times t squared plus b times t plus c, then the velocity function, what would be the derivative of that? Like if you take the derivative of at squared plus bt plus c with respect to time, what's the derivative of t squared?
2t.
Right. And we've also got the a still there, so 2a times t. And then the derivative of bt?
Just b.
And the derivative of c?
That'd be 0.
Right. And so you get v equals a constant times t plus a constant. That's going to be a straight line. Whereas the position graph that leads to that is a quadratic function, a parabola. So one of the important results of this is that if the position function is a quadratic function, a parabola, then the velocity graph will be a linear function. But if you take a look at this position graph does not really look like a parabola. If anything, it looks kind of like a cubic. In fact, we might sketch out something like, if we continued this, we might have something like this, a cubic function. The derivative of a cubic function would be a quadratic function. So since the position graph resembles a cubic function, I would expect the velocity graph to resemble a quadratic function, a parabola shape.
Okay, that makes sense. Thank you.
Mm-hmm. And actually, if we take this a step further, if you want to find the acceleration, we would just take the derivative of the velocity one more time. So what's the derivative of 2at?
2a.
Yeah, just 2a. And then the derivative of the plus b?
0.
Yeah. So this trifecta shows up all the time. You'd have a quadratic function for position, a linear function for velocity, and a constant for acceleration. And that goes in both directions. If the position is quadratic, then the velocity is linear and the acceleration is constant. In reverse, if the acceleration is constant, then the velocity must be a linear function and the position must be a quadratic function. So this is going to show up anytime the acceleration is constant, such as when the total force is constant. And so this is where the kinematics equations that you've seen come from. They just come from assuming the acceleration is constant. Therefore, the velocity has to be a linear function and the position has to be a quadratic function. Any other questions on the position and velocity graphs so far? Then let's draw out the acceleration graph also. Acceleration is the derivative of velocity. So we really just need to look at the slope of the velocity graph. For instance, from 0 to 1, from 1 to 3, from 3 to 5, what are the slopes of all those green lines?
0.
Yeah, so that means we should expect the velocity graph to have slope 0. Or sorry, the acceleration graph should have slope 0. Or sorry, value 0. Since the velocity graph has slope 0, the acceleration graph has value 0. Which kind of suggests that there's no change in velocity, but that's not true. The velocity does change. It's just that it's these sudden changes. Formally, what that means is if you've got the position graph changing its slope suddenly, then the velocity graph changes its value suddenly. And a sudden change in value like that, a gap in the graph, technically means that its derivative is undefined at that point. So at 1 second, there is no acceleration. At 3 seconds, there is no acceleration. At 5 seconds, there is no acceleration. But again, that's not really very realistic. It'd be more realistic to assume that the velocity changes very quickly, but not instantaneously. So let's correct that. Let's say the velocity is not changing instantly. It's changing over some period of time, just a very short period of time. So let's assume that we have very sudden but not instantaneous changes in velocity. Something like this. That's going to be much more realistic. Velocity in real life does not change instantly. It can change very quickly, but it doesn't change from one to another in an instant. So I think it would be more realistic, even if it's not what the original graph showed, to have these connected by very steep but not vertical lines. In that case, we can actually find accelerations, or at least approximate them. Like if you look at just this section of the velocity graph, what do you notice about the slope of just that section? It's negative, right? We've got this very sudden downhill slant and also very steep. So if the velocity has a very steep negative slope here, we should expect the acceleration to have a very large negative value. So for a very short amount of time, the acceleration is extremely negative. And likewise here, at 3 seconds, from a little bit before 3 seconds to a little bit after 3 seconds, we've got a very sudden decrease in velocity. So we should expect a very sudden, very strong negative acceleration. Likewise, at 5 seconds, the velocity changes from a little bit negative to much more negative. That's a very sudden and strong negative change. So we should expect a very steep, very sudden negative acceleration, but only for that very short amount of time. Any questions on that so far? And then after that, what do you notice about the slope of velocity from, let's say, from 5 seconds to 7 seconds?
It's positive and getting less steep over time.
In fact, at let's say 7.5 seconds, 7 1/3 seconds, something like that, it looks like velocity reaches a maximum. If that function reaches a maximum, what does that tell you about its derivative?
It's 0.
Yeah, so we know at that instant in time, the acceleration has to be at 0. And then we can split it up into, as you said, the positive region and the negative region. So in this entire region from, let's say, from 5 seconds to about 7.5 seconds, the acceleration is positive. After that, it looks like the velocity graph is decreasing. So that's going to be a negative acceleration. We can also tell this from the original position graph. From 5 to 7.5, the position is concave up. That means its second derivative is positive. From 7.5 to 10, the position graph is concave down. That means its second derivative is negative. So we know that the acceleration graph has to go from positive to 0 to negative. Probably starting off at a fairly large positive, then getting to 0, and then a fairly large negative, because the velocity graph goes from fairly steep upwards to getting less and less steep, then flattening out, then a little bit negative slope, and then a much steeper negative slope. So we can expect the acceleration graph to change from very positive to a little bit positive to 0 to a little bit negative to very negative. And I think a straight line is a safe assumption here, specifically because we were treating the position graph as a cubic, so its derivative is a quadratic function. So this is a quadratic function for velocity. What's the derivative of a quadratic?
Linear.
Right. So a cubic position graph leads to a quadratic velocity graph, which leads to a linear acceleration graph during that period of time. And again, this is just a rough sketch. We're not really filling in exact numbers. We're not calculating what the derivative is, but just using the shape of the graph, we can get at least a best guess as to where it's positive, where it's negative, where it hits maximums and minimums, where it passes through zero. Those, I think, are the important things to look for. Any other questions on this graph? All right, and then you can also go in the other direction. If you have the acceleration graph, you can backtrack and say, these values tell you the slope of the velocity graph, and sketch the velocity graph. Then look at the velocity graph and say, these values tell you the slope of the position graph, and draw the position graph. So if you want some practice on that, take a look at the integrals worksheet on that same website, mathandcheese.org/P7math. Let me put that in the chat again. math.andcheese.org/P7math. If you go there and click on derivatives, you'll get to this worksheet. If you click on integrals, you go to another worksheet that has a similar setup, but in reverse. Here's the acceleration graph, backtrack to find velocity, then backtrack again to find position. So give that a try. We can try that next time if you want. But I'd also like to look into the kinematic equations today as well, because that's very closely related to what we've just been doing. In fact, the kinematic equations are based entirely on this concept right here. The idea of quadratic function for position, linear function for velocity, and constant value for acceleration. In fact, let's try that in reverse. Because here we were just sort of assuming we had a quadratic function for position. But if we reverse that, let's say assume we have a constant function for acceleration, because that's often what we know. For instance, what causes acceleration? What has to be happening to an object to make it accelerate?
A force has to be applied.
Right. You apply a force, you get an acceleration. And specifically, the sum of the forces, the total force acting on the object, equals mass times acceleration. And that's what we usually call Newton's second law. Force equals the total force on the object equals mass times acceleration. So let's say that's constant. Then the acceleration is constant also. And that's an equation. Acceleration equals constant. From that, we can build the idea of velocity. If you know the acceleration, how do you calculate velocity? How are those quantities related? Acceleration is just the derivative of velocity, right? How do you undo a derivative? What's the opposite of taking the derivative of a function? Yeah, the antiderivative or the integral. So we can find the velocity by just taking the antiderivative of both sides. Velocity is the integral or antiderivative of acceleration dt. And if you had some function for acceleration, you'd have to integrate that function. But in this case, we're assuming acceleration is constant. And what's the integral of a constant? Yeah, or in this case, at, since t is the variable of integration. And since this is an indefinite integral, it could be any starting point. We need a plus some unknown constant, since we're looking for all possible solutions, not just one solution. The thing is, though, we can actually find out what that constant is by plugging in some value for time. And what's the easiest time value to use? We just plug in 0, right? You plug in 0 for time, we get speed, the initial speed equals acceleration times 0 plus c. Acceleration times 0 is just 0, so we get initial speed is c. In other words, that constant there represents the initial speed. So our equation for velocity is just velocity at any time equals acceleration times time plus the initial speed. And that's what we call that's one of what we call the kinematic equations. The kinematic equations literally are just a bunch of equations describing motion that can be used anytime we know the acceleration is constant. And this is one of them. If the acceleration is constant, then the velocity at any time must be acceleration times time plus the initial velocity. And a very useful way of thinking about this, acceleration is just change in speed over change in time. So if you multiply acceleration times time, what sort of quantity do you get? It might help to think of it in terms of units. Acceleration is measured in meters per second squared. You multiply that by seconds, and what's the units that are left?
Meters per second.
Right, you're left with just meters per second, which is a velocity, specifically the change in velocity. So the acceleration times time is just the change in velocity. You're adding that to the initial velocity, and you get the final velocity. That's really all this equation is saying. You've got your starting velocity plus how much your velocity changes because you're accelerating, and the result is your final velocity. We're just writing it in function notation. Any questions on that so far? So let's take this one more step. We've got a formula for velocity. How do we get from there to position? Velocity is just the derivative of position, right? So how do we undo that derivative?
Take the integral.
Yeah, take the integral one more time. Velocity is just the integral of velocity, or position is the integral of velocity. And if we fill in the, again, in whatever formula you have for velocity, that's what you'd be integrating. In this case, with the constant acceleration, the velocity formula is just acceleration times time plus initial velocity. So we can fill that in. And if we can integrate that, we'll have a formula for position. Integral of AT is going to be what? Acceleration is just constant, so we can pull that out, right? But what do you get if you integrate just t? T to the first power. What's that integral going to be?
Is it half t squared?
Yeah, because this is just t to the 1 power. Anytime you're integrating just t to a whole number power, or any power really, doesn't even have to be a whole number. Integral of t to a power is going to be t to that power plus 1 divided by that new power. So t to the 1 becomes t to the 2 divided by 2. And the divided by 2 we can just combine with the acceleration. So half the acceleration times time squared. And then initial velocity is a constant. Integral of a constant is just that constant times time. And then we also need plus a constant as well, since this is an indefinite integral. What do you suppose that constant represents, though?
The position at time 0?
Exactly, because again, if you plug in 0 for time, these terms drop out. You're just left with c equals the position at time 0. So that's just x initial, the starting position. So that's another kinematic equation we can use. that the position as a function of time, let me actually write that in function notation. Position as a function of time is always going to be half the acceleration times time squared plus initial speed times time plus starting position. As long as the acceleration is constant, this is valid. And you can think of this in a very similar way to how we're thinking about velocity. If you split this into pieces, you've got a piece representing where you start, the initial position. And then we've got a speed times time. What do you get if you multiply speed times time? Again, if you take a look at the units, you've got meters per second times seconds. What does that become?
Just meters.
Right, just meters. So speed times time is a distance. And it's useful to think of that as just the distance you would travel if you were going that speed the whole time. So this is how far you travel because of your initial speed. Then this other term, acceleration over 2 times time squared, that's meters per second squared times seconds squared. That also works out to meters. So this is also a distance. It's specifically the extra distance you travel because you're accelerating. So all this equation is saying is your starting position plus how far you travel because of your initial speed plus how much extra you travel because you're accelerating equals your final position. This is still basically a final x equals initial x plus delta x. It's just that the delta x is made more complicated by the fact that the speed is changing. Any questions on that equation so far? And it looks like this has 5 variables, right? We've got initial position, final position, starting speed, acceleration, and time. 5 variables. So if you know any 4 of them, you can immediately solve for the 5th one. Might involve a quadratic formula because you've got a time squared here, but it's always possible. If you've got 2 unknowns, then you may have to combine that with another equation to get more information using substitution or elimination. But in general, as long as you can set up as many unknowns as you have equations, then you're good to go. There's also one more kinematic equation that's often used, often called the time-independent one. And specifically an equation that doesn't have t in it. The idea is there are many situations where you don't know how much time a process takes, and you don't really care how much time the process takes. You just want to figure out how far an object travels or how much its speed changes between the time it's at this location and the time it's at this location. But you don't know how much time it takes, and that's not what you're trying to find. So you can get another equation by combining these 2 equations with substitution. Specifically, if you isolate t in this equation, if you solve this equation for t, you get what? T equals v final minus v initial divided by acceleration. And then substitute that into the time in the other equation, then you can get a new equation that doesn't involve time at all. And it looks complicated at first, but it can be simplified to, if I remember correctly, v final squared, or one way to write it anyway, is v final squared equals v initial squared plus 2 times acceleration times delta x. So this is another very useful equation. If you know the acceleration is constant, then the final squared speed is the initial squared speed plus 2 times acceleration times distance traveled. So this can be a very useful formula if you don't know how much time a process takes and you're not trying to find how much time it takes, but you want to know, for instance, how much the speed changes while an object travels along a certain distance. For instance, maybe you've got a plane taking off from a runway, you know it starts at speed 0 and it has to reach some final speed that's fast enough to take off. And you want to know how long the runway has to be to make this work. In that case, you know initial speed, you know a final speed, maybe you know the acceleration the engines can provide, and you're trying to find distance, how long the runway would have to be. So again, that's just a situation where we don't know time, we're not trying to find time, but we want to know how the other quantities are related. in general, for situations like this, I would recommend writing out a list of all the values you know, all the values you're trying to find, and then see if you can find, or just write out these equations, the kinematic equations, and look for which one or ones link those values together. If you can get as many equations as you have unknowns, then that should be a system of equations that can be solved. Any other questions on that?